When maglev starts running at its full speed, it hides its tires like airplanes and runs completely in the air, which has a speed of 600 kilometers per hour. Friction is a huge area of maintenance inside normal trains, but there is nothing like this in this train. First comes the permanent magnet, then the electromagnet, and above all the superconducting magnet, which is very powerful. And this magnet is used in maglev trains. Engineers of Japan made this train in 1997, and today there are some other countries which are using them. There are 3 requirements to successfully operate this magnetic train. First, propel. It means how to propel the train. The second is levitation, which is when the train runs at a speed of 600 kilometers per hour, a large region of mechanical contact friction is formed, due to which fire can occur. Then it brings the train from the surface to the air with the help of a magnet. And number 3 is guidance, guiding the train on a path after successful levitation. First of all, let's talk about superconducting magnets' magnetic levitation. The train requires a strong magnetic field. As strong as the magnetic field of a magnet, the train will get the best lifting and propelling force, which will provide a good speed to the train. There are some limitations of the electromagnet. When current flows more than its limit, then it fails due to heating. But this is not the case with superconducting magnets. Conductors are also used in superconducting magnets, and the temperature of these conductors is kept below their critical temperature. The resistance of the conductor attached to the superconducting magnet is 0, due to which the heavy current flows easily in this conductor without any hindrance. Now, if the resistance of the conductor in this magnet is 0, then once the superconducting magnet is charged with an exciting coil, then the short-circuited coil inside it will store the charge forever, and then we'll never need to supply it. Inside the short-circuited coil, there is a trapped DC current. It's circulating type, which provides a strong magnetic field. The value of this DC current is very high. Almost 700 kiloampere current flows through it. And how much this current is? Well, you can guess from the fact that a current of 0.5 ampere can kill a person. And this is the reason that superconducting magnets are very powerful and efficient electromagnets. Now, this much heavy current will flow in the conductor of superconducting magnet, and then it is a general thing that there will be a lot of heating. That's why cooling is provided to keep it in superconducting stage, and liquid helium refrigerant is used as a coolant. When the liquid helium comes out with the heat of the conductors, it evaporates from the heat of the conductor. Then a helium compressor is used to convert it back to liquid. Now, one thing is to be noticed here, that the resistance of the conductor used in superconducting magnet is almost 0, due to which this conductor is very heat sensitive. So it can also absorb the heat outside in the environment. That's why the radiation shield is used to protect it from the outside heat. When the superconducting magnet is protected by radiation shields, then again a problem arises here. Due to the conductor of the superconducting magnet, eddy current will be produced inside the shield, which will again become the reason of heating of the shield. Eddy current is a current whose nature is circulating in type. No one needs this current, but it starts circulating on its own due to the magnetic field. So here the radiation shield will also need cooling, and it is provided with liquid nitrogen cooling. To prevent the external radiation from coming inside, a vacuum is created in the middle of the radiation shield so that it can stop the outside radiation properly. In this way, a superconducting magnet is prepared, and it provides excellent magnetic field in its superconducting stage. And with a set of 4 such magnets, a protective shield is prepared for them, and we have used one cooling system for these 4 magnets. In this way, a complete unit of superconducting magnets is prepared, and many such units are set inside the train on both sides. If you have noticed here, superconducting magnets do not require electricity, but the propellant we have provided for cooling requires high electricity. Now, after setting the superconducting magnet in the train, the first thing we need to do is to propel the train. How do we achieve this? For this, the electromagnet is used and a string is made by putting many magnets in a series. This electromagnet is responsible for moving the train. So it is called propelling coils, which moves the train in a very interesting way. power supply is done in propelling coils in such a way that if one coil is working as north pole, then the nearby one will work as the south. In this way, alternate power supply is given to these magnets, as you can see. For those of you who do not know, let me tell you that the electromagnet is such a magnet whose field can be changed by us. We can make the North Pole south and the South Pole north with our will. But the poles of permanent magnets are completely fixed. In this way, these magnets are set inside a guided way on both sides of the train. Now here it will be very interesting to see how a superconducting magnet and electromagnet together exert propelling force on the train. It is to be kept in mind that superconducting magnets cannot change their field. Their north and south poles are absolutely fixed. It works like a permanent magnet. Now let us see the behavior of one side of these two types of magnets. How the net force works here. You can see the force exerted on all these magnets, and if we calculate this net force, then this net force will be applied on the train in the forward direction, like both these north pole will repel each other. From here, this south pole will attract this north pole. So in this way, the force acting on the train is in the forward direction. In the same way, the net force of all these magnets is in the forward direction. As the train reaches the next position, the polarity of the propelling coils is reversed, and again, the net force will be in the forward direction. And in this way, the train moves forward by switching propelling coils, and the train speed can be controlled by this switching speed only. We have successfully achieved propelling. Now comes the matter of magnetic levitation, in which way a maglev is lifted in the air. For magnetic levitation, H-shaped coils are used, inside which no power is supplied. It works in the same way as the winding which is attached to the motor. This H-shaped coil is just a wire and nothing else, inside which there is no supply. Now you're probably wondering, how does it work? The way that these H-shaped coils are set inside the guide, we must remember Faraday's law, which states that when a coil is placed inside a magnetic field, it experiences some force. For example, if we rotate this permanent magnet between the coils placed on both these sides, then the magnetic lines coming out of this magnet will cut these coils, due to which some EMF will be induced in them. Let us apply this concept to maglev. If we look at the behavior of superconducting magnets placed on both sides of the train, both the magnets together work like a big magnet. To make it a little simpler, as an example, we consider these two superconducting magnets as permanent magnets of this type. When this magnet travels forward, the magnetic lines of the magnet will cut the H-shaped coils located on the side. According to Faraday's law, EMF will be induced inside both the loops of these H-shaped coils. It is visible to you in the same direction, but when we straighten the coil, the force exerted on it will be in the opposite direction. This means that the net EMF induced inside the coil due to permanent magnet will be zero. When the net EMF will be zero, then why did we install the coil? Its reason is that if we set the permanent magnet a little lower, then the lower loop of the coil will face more magnetic lines, due to which it will induce more EMF in comparison to the upper loop, because of which a current will start flowing inside the coil, and as soon as there is a current flowing in it, poles will be created inside the coil, south pole on the top and north pole on the bottom. Now if you look carefully here, these two north poles will repel each other, due to which the train will get the lift force upwards. If this force is more than the gravitational force, then the train will levitate. That is, it will come in the air. As the train levitates, the force on the coil will reduce and the magnets will balance. Now here another problem gets created. When the train runs slow, there will be very less EMF induced in the H-shaped coils because the magnetic lines will cut them very slowly. So when the train starts running, it cannot levitate. Therefore, when the train starts and stops, at that time, there are tires inside it, which it uses, and as it picks up speed, it hides its tires like an airplane because now the magnetic field becomes strong, which levitates the train successfully. Now comes the last step in which the train has to be guided, and for this it is very important that the train should be in the center, so that it does not touch the side. Otherwise anything can happen at such a high speed. For this, a very simple technique is used. For this, H-shaped coils are connected with the help of interconnecting coils. When the train is in balanced condition, equal EMF will be induced in both the coils, due to which there will be no current flowing in the interconnected coils. But we assume a condition that if the train moves slightly to the right, then in this condition, different EMF will be induced in both the coils, because of which the connecting coils start flowing current in it, due to which the lower loop of both the coils and the pole of the permanent magnet will put a lot of stress. High current will flow in the right side of the coil, to which the south pole here will become very strong, and less current will flow in the other side coil, whose north pole will be weak. These two south poles will repel each other. The magnet will again come to the center, and as soon as it comes to the center, the current flowing in the connecting wire will become zero. So, in this way, the train is guided. Now it is a matter to think that what will be the source of electricity inside the maglev. For this, the engineers used inductive power collection technology, which we also call wireless electricity. One coil is set on the ground under the train, and the other coil will be set inside the train. When supplied to the ground coil, it will generate a magnetic field around itself, and the same magnetic field will reach the coil placed inside the train, which will supply electricity inside the entire train. Now, if you have seen right here, how many magnetic field lines can become a danger for the passengers traveling in the train, and especially the magnetic field of the superconducting magnet, which is very powerful. So for security, a magnetic shield is placed on both sides of the train, which does not allow the magnetic lines to reach the passenger. The speed of this train is 603 kilometers per hour, with which a great world record has been made. So in this way, the magnetic levitation train works. If you like this video, then please give us your support, subscribe to the channel, and like the video. Thank you for watching.